Can you see the screen? Yes or no?
Yes, sir.
So in the last class, we are actually discussing about the quantum numbers. What we have done is we have done about the principal quantum number, and we have also done about the azimuthal quantum number. What that have done in the last class. And now today I took a table, see how the what orbitals are present. Table will be drawn to this. So we have seen that there are four types of subshell: S, P, E, and F. These are the four different subshells that are present. The S, P, D, F, and if the L value is 0, then it is an S subshell. L is equal to 1, then it is the P subshell. Or L is equal to 2, that is the D subshell. And or L is equal to 3, that is your F subshell. So these are basically the subshells that we have. So now if I make a table for suppose with the N and the L values, suppose N, and we write L. So these are the subshell designation. Subshell designation. Subshell designation. Then we write number of electrons. Number of electrons. Then not number, rather the max number of electrons. Max number of maximum number of electrons. And finally the number of subshell. Yeah, okay. Number of subshell. Okay. Number of subshell in a cell. Maybe to join anyone is. So if the value of n, if it is equal to 1, if the value of n is 1, then what will be the value of s? What will be the value of s? The value of s will be 0, because we have already seen that for n is equal to 1, the possible value of l is only 0. That is, for the value of n to the 1 by l is going to be 0. So then the subshell designation, it will be called 1s. Called 1s. Because 0 mane s subshell. We call it 1s. Now what is the maximum number of electron over here? What is the maximum number of electron in this subshell? Over here, so the formula calculate, or let's do the rest first. Suppose now n is equal to 2. The value of n is 2. Then the possible values of L are 0 and 1. These are the two possible values of L. 0 and 1. These are the two possible values of L. 0 and 1. So 2 and 0, 0 mane S subshell. That's why it is called the, and 2 and 1, it is called the P subshell. 2S and 2P. Then suppose if we have the value of n, if the principal quantum number is 3, then what are the possible values of your L, the possible values of L can be 0, 1 and 2. These are the possible values of your L. So 0, 1 and 2, these are the possible values of your L. So I will write it as L, 0, 1, 0, 1 and 2. That's why the possible values can be 3s, 0, then we call it 3s, 3p. And if the value of L is 2, we call it 3D or subset. That's why this subset is designated as 3D. Then you have, suppose, what if the principal quantum number is 4? Then what are the possible values? 0, 1, 3. These are the possible values. We write them. The value of L can be 0, 1, 3. So 0 means S subshell. That's why I call this 4S. 1 means 4P. 2 means 4T, 4F. This is how the subshells are designated. So this is how we are going to designate each of the subshells. So we do not call them 40 like this. We say them 4S, 4P, 4T. So from now onwards, we will be using these terms also. When you write the electronic configuration, this 1S subshell, 2P, 3P, all these things will be seen as we move on to the further part of the chapter. So now the thing is, what about this thing? The maximum number of electrons. So the formula to calculate the maximum number of electron in a subshell, let's write it over here. Max number of electron in a subshell that is equal to 2 into L plus 1 into L plus 1 L plus 1. Over here, if we calculate, what will be the value? Now the value of S money, the value of L is 0. So that means this is going to be 2 into 0 plus 1. That is equal to 2. So the 1s subshell can have a maximum number of 2 electrons. What about the 2s subshell? 2 into, here also the value of L is 0. That's why 2 into L money 0 plus 1. That is equal to 2. So the 2s subshell also has maximum number of 2 electrons. In fact, we see that for S subshell, whatever, be it 2s, 3s, 4s, 5p, 5s, whatever, we get that the maximum number of electron is 2 in the S subshell. What about the P? For the P, you see, the formula is 2 into 12 plus 1. That is, P money, the value of L is 1. So the value of L is 1 over here. So that is why 2 into 1 plus, that is equal to, we will get 6. So this 2p subshell has a total number of 6 electron over here. So now 3s we have already done. So 3s, how many electrons will be there? As it is an S or subshell, that means here the maximum electron can be 2 only. So for 3p, again here the value of L is 1. So 2 into 1 plus 1, similar calculation we will get that in the 3p subshell also we get that the maximum number of electron is 6. What about this 3d? The 3d you see 2 into 2 plus 1, that is equal to 10. So this 3D subshell can has a maximum number of 10 electrons. Now let's do it for 4s. For 4s, 2 electrons maximum because it is an S subshell. Whatever P be there, P money it is 6 electron maximum. D subshell money 10 electrons at max. Because see, whether be it 3D or 4D, ultimately the value of L is same in both the case. So that is why 3D also has a maximum of 10 electron, while 4D also has a maximum number of 10. Because over here, the max electron depends upon the L value. The max electron is dependent on the L value. Okay. Now you get 4F over here. So what we make out of it? So in this case, you get 2 into 3 plus 1. That is equal to 14 electrons. There is a total of 14 electrons. 2 into 3 plus 1. That is 14 electrons. So this is how the subshells has the max number. So now if you see the number of subshell in a shell, the number of subshell in a shell. So that means the first shell, that is n is equal to 1, has only one shell, one subshell, one S, that's it. Only one subshell is present in the first shell. For n is equal to 1, only one subshell is present. But you see, for the second shell, that is for n is equal to 2, we have two possible subshells, 2s and 2. So there are two subshells possible for n is equal to 2. What about n equal to 3? When the value of n is equal to 3, that is for the third shell, you have three subshells, 3s, 3p, and 3t. So there is a total of 3 subshells for the third shell. Then what about the fourth shell? For the fourth shell, you have 4 possible subshells, 4s, 4p, 4d, 4f. So there is a total of 4 subshells. And if you see, what is the summation of the electrons? So here in the first shell, maximum 2 electron can be present because only one subshell is present, so only 2 electron is present. But see, in the second shell, 2 subshells are present. One contains maximum 2 and another has maximum 6. So that means overall 8 electrons can be present in the second shell, 8 electrons at max. In the first shell, we have just 2 electrons. For the third orbit, how many electrons maximum can be present? 2 plus 6 plus 10. That is equal to at max 18 electrons. At max we can have 18 electrons. For the fourth orbit, how many electrons can be present maximum? That is 2 plus 6 plus 10 plus 14. That is equal to at max the fourth orbit can have 32 electrons. So now you can see that this value is in complete agreement with the principal quantum number that we did see. 2n squared. The first shell has 2 electrons, second shell 8 electrons, the third shell 18, fourth we have 32. And like this way also, when you are calculating with respect to the subshell, then also we are getting the same value 2, 8, 18, 32. So that's why this table is important for the sake of understanding that how the shell and the subshells are designated, how many electrons can be present in each of the subshells. So is it clear to every one of you? Yes or no?
Yes.
Yes, sir.
Did anyone say something? No.
Yes, sir.
Okay, it's clear. So now you can understand that principal quantum number and residual quantum numbers we have completed. We have done these two kinds of quantum numbers. So now we see. Achha, by the way, who are there in the class? So one is Ayush. And just tell me your names of the students who are in the class. Can you tell me your names? Because I cannot see the tab of the students that are present. So that means now initially we knew that this is one shell, n is equal to 1. Then you have n is equal to 2, n equal to 3, n equal to 4. So till now we had known that this is how the energy levels of the shell are going to be arranged. First shell, second orbit, third orbit, fourth orbit, like this. The first energy level, second energy level, third energy level, fourth energy level. How it was arranged, we had known till this time. But now we are seeing that no, there are further sub-classification. So inside the first shell, we have only one subshell, that is 1s. But the second orbit is sub-classified into two different subs. Now, this one line will basically split two other. That is one is 2s and another one is 2p. Similarly, the third orbit, you can see that the third orbit has 3s, 3p, 3t. That means this will split into three lines. And the fourth orbit will split into four lines. Now, understanding that you had from before, that is that no, each of this orbit is also actually divided into not only just one line, but they have different subshells inside them. So that means this is your 1s, this is your 2s, 2p. So inside the second orbit, you have 2s and 2p. Inside the third orbit, you can have 3s, 3p, and 3t. Inside the fourth orbit, you can have 4s, 4p, 4t, 4p. This is how the shells are classified into subshells. Okay. So that's it. So this is about the azimuthal quantum number. Now we'll come on to the magnetic quantum number. Now let's move on to the magnetic quantum number denoted by M. Let's see the magnetic quantum number, which is denoted by M. Number 3 is our magnetic quantum number. Magnetic quantum number denoted by M. Okay. So now what does the M tell? What can you actually get? What knowledge can you get from this M? So M actually helps us. M helps us to calculate the number of orbitals. The number of orbitals. Number of orbitals present in a subshell. Present in a subshell. So M helps us to calculate the number of orbitals present in a subshell. So we can get to know about the number of orbitals that is present. Now we'll get to know what orbital is firstly, right? So what can be the values of L? It can have what can be the values? The values can be of minus L to plus L, minus L to plus L. So that means for L is equal to 0. So if the value of L is 0, then what will be the value of M? The value of M can be minus 0 to plus 0. So it's basically there is nothing called minus 0. It's simply 0. But see, if the value of L is 1. Then what can be the values of m? Minus 1, 2 plus 1. That means it can be minus 1, 0, plus 1. Then if you see, what if the value of L is 2? And L2 means the D subshell. If the value of L is 2, then it is referring as to the D. So the value of M can be minus 2, minus 1, 0, plus 1, plus 2. L is equal to 3. Then what can be the values of M? M can be minus 3, minus 2, minus 1, plus 0, plus 1, plus 2, plus 3. So that means for L is equal to 0, only one value is possible. That means only one orbital can be possible. Only one orbital is present for L is equal to 0. For the value of L, if it is equal to 1, then we can have 3 orbitals. 3 orbitals. If the value of M is 2, then we can have 5 orbitals. 5 orbitals. And if it is 3, then it can have a total of 7 orbitals. Okay. So till this much, is it clear how we are getting the values of M from the value of L?
Yes.
So then, now the question is, what is orbital? We are saying that one orbital, two orbital, but what actually do we mean by orbital? Let's write down the definition of orbital. So an orbital, that is the magnetic quantum number, actually gives us an idea of this spatial arrangement of the substance. So the magnetic quantum number gives us an idea. What does it tell us? About the spatial arrangement. About the spatial arrangement. Spatial arrangement of the subshell. Of the subshell with reference to, let's write it the full spelling, with reference. Now we do not write always the full spelling of with reference to. We just write WRT. WRT only means with reference to. You can use it in any science or math whatever. With reference to Cartesian coordinate. Cartesian coordinate. So these different orientation are called orbitals. So let's see what the definition is. Suppose now say I told you in yesterday only that you have the x-axis and the y-axis. You have done graph x-axis and y-axis. Other than this, and you know that x and y-axis are perpendicular to each other. So the two axes are perpendicular. Now there is also a third axis. Whenever we are drawing a three-dimensional object, there has to be three axes, length, breadth, height, all the three axes has to be there. So this is the third axis. This is called the Z axis. So this is the X axis, Y axis, and the Z axis. The Z axis is again perpendicular to the X or Y axis. So it's as if the X, Y, and Z are all perpendicular. So now you look at the corner of the room. If you look at the corner of the room, what you can see is, you see that the floor has two lines, right? The floor has two lines. If you look at any corner of the room, you can see that suppose the floor is going on one side, it has like two sides. So that is the floor is the X or Y axis, okay? So the two sides of the floor, that is the X or Y axis. And the wall that is going above, that is the Z axis. So you see, all the three are perpendicular to each other. Because see, if you see the floor, your floor is somewhat like this, that looks like this. Here you have, this is the floor. Let's make some marbles and all so that you can understand. This is the floor. So suppose this is only your x-axis, the x-axis, and this is the z-axis. Okay. And now when you are looking at the floor, you see from here, this corner, there is also the wall is also there, which reaches till the ceiling. So this is, you see, it's perpendicular to x and z. So this you can consider to be your y-axis. So you can always interchange their position. If you wish, you can call it z, you can call this y, or you can even call this y. That's up to you. You can interchange the position of the notation of this x or y. But yes, so this is how the x and y and z. The floor is a very good example of understanding the three-dimensional geometry, the three-dimensional Cartesian coordinate. So now obviously it's in the positive side. Now if you want to make it in the negative side, then you just extrapolate this line till this much. This will be extended till this much. So this, now you get your graph that I have drawn. Okay. So is it clear from the floor thing how we are getting the three-dimensional thing? Yes or no? Hello, is it clear?
Yes, sir.
Yes, sir.
So this is the three-dimensional geometry, the x, y, and the z axis. So now this is only what is being said, that the magnetic quantum numbers actually tells us how the subshell is arranged. That is it like this? Is the subshell arranged like this? Is it like this? Or is it arranged in this way? Or is it arranged somewhere in the between like this? So what is the position of this different subshell? That is what is told by the magnetic quantum number. And this different arrangement or the orientation, that is known as the orbitals. So these different orientations is known as the orbital. Now we have to draw the structure of orbital. Now as you can see that these orbitals are all three-dimensional in shape. The orbitals are three-dimensional in their shape because it's a three-dimensional concept. Whenever we are applying x, y, and the z axis, it's a three-dimensional concept. But my screen and your paper is a two-dimensional. It's two-dimensional. Your paper is a two-dimensional. But you have to draw a three-dimensional object on a two-dimensional paper. So it's difficult to understand the real shape of orbitals if I just draw it at first. So let me go to a website and show you first actually the shape of the orbitals. Then we will come and draw these shapes of orbitals. So let me just go and draw the shape of orbitals. I hope you can see the screen.
Yes, sir.
Yes, sir.
So let's write shape of the orbital. Shape the orbital. Here. There are many websites. You can also see wherever you are studying. Let us see this diagram also. First, let me just open it in a new tab. How this one? Well, it is myself. This is not. This is what I will also do. Now it is difficult to understand the shape by looking into this. You cannot see that whether it is a 3D or not. Everything is appearing like a 2D only. And moreover, they have not drawn one axis. This is not. This one is good. See, this is the d orbital. So first we have to see the shape of the s orbital. S orbital. So see, I have told you when I taught you yesterday about the azimuthal quantum number. There I had told you that S subshell is spherical in its shape. So the S subshell is basically spherical. It is looking like a football. So over here, now you can see. So this is the shape of the S orbital. Can you see the screen? Can you see
Yes,
the
sir.
screen? So you see the X, Y, and the Z axis. You see all the three axes, X, Y, and Z axis. And see, it's a spherical. It is looking like a football from on the side. Okay, so now can you understand the shape of the S orbital? How our S orbital looks? Yes or no? It's the shape of an S
Yes.
orbital, clear to everyone?
Yes, sir.
So these are the three axes as you can see. The X, Y, and the Z axis. X axis, Y axis, Z axis. And this is how all the three axes are perpendicular to each other. They all make 90-degree angles with each other. Okay. And it looks like a football. So this is the shape of S orbital. First, let us understand all the shapes, then I will draw them. So this is one orbital. And this is the second, this is the 2s orbital. So this one was the smallest, 1s. This is your 2s. So it is a bit larger in size. Then this is a 3s, more bigger in size. Okay. Now the thing is, actually, although they do not look like a football, actually the orbitals look like this. It looks like this. This is how the orbitals. So what you can see from there is that it is made of dot-like structures, right? You can see all dots over here. So what does the dot represent? The dot represents the probability of finding the electron. Greater the number of dot, greater is the probability of seeing the electron over there. So as you can see that the blue dot is like very congested in the middle in this part. So in the
Yes.
origin, near the origin, the blue dot is highly concentrated, and as you are going away from the origin, you see the blue dots are becoming much more farther from each other. So that means, so if you do the average, you can see that it is found, the electron can be found near the origin. The more further you move from the origin, the probability of finding the electron decreases, because we cannot actually exactly say where the electron will lie, because it will be a violation of the Heisenberg's principle. Heisenberg principle says that we cannot exactly pinpoint the position of an electron. That is why we have to think in terms of probability. That there is a high chance that electron can be present in this region. Electron can be present in this dotted region. There is a probability of electron being present, but we cannot exactly pinpoint and say that this is the electron, because then Heisenberg's principle will be violated. So this is how the orbitals. So it's basically just a probability distribution chart. So it's a probability distribution chart where you are seeing the dotted lines. The dots represents the probability. The more concentrated a dot appears, higher is the probability of finding the electron at that particular position. So this is for the 1s orbital. Then you see the shape of 2s orbital. The 2s orbital you see, in the 2s, you see one, there is a blue dot, and then outside you have a red dot. So these are basically the two different subshell. 1s, so we have the 1s inside. So the blue dots represents the 1s subshell, whereas the red dots represent the 2s subshell. And you see in between the 1s and the 2s, that is in between the blue and the red dot, there is a total empty region. That means in those empty region, there is no probability of finding the electron in that empty region. Okay, so this is how the 2s orbital is going to look. Then let's see the structure of 3s orbital. So this is the structure of 3s orbital. So blue, then red, which is the 2s, and then further you have another blue circle, the 3s circle. Okay, so this is how the orbitals actually look in real life. Although no, in real life they even do not look like this. But this is a quite an accurate description of how the orbitals really look like. Okay, so it's quite beautiful to look at when it's. So this is the shape of the s orbital. S orbitals are spherical in shape. And by spherical, what do we mean? I hope it is clear to everyone. Is it clear to everyone? The shape of the orbital.
Yes, sir.
So s orbital is spherical in shape. Now let us see the shape of the p orbital. Now let us see the shape of p orbital. P orbital. Okay. Now see, p orbital can have, when we did about the p subshell, you see p can have three values. P can have three different values: -1, 0, and +1. That means I told you that there are three possible orbitals for the p subshell. So the p subshell can have three orbitals: -1, 0, and +1. So this -1, 0, and +1, they do not represent any numeric value. They just gives us an idea that p subshell has three different orbitals. So this is how they look. This is the px orbital. So if you see in this box, so you see over here the orbital is lying directly on the x-axis. So the orbital is oriented directly on the x-axis. It is touching the x-axis. You see the y-axis and the z-axis is free. Nothing is there on the y and the z-axis. These two axes are completely free. The orbital is entirely situated on the x-axis. The orbital is entirely situated on the x-axis. So that is why it is called px. Then what is py? So another possibility can be when the orbital is situated totally on the y-axis. So that is your py. And see, nothing is touching the x and y-axis. Nothing is touching the x and y-axis. Okay, so this is the shape of your py. They look exactly similar. It's just the axes are changing. Then this is a pz. So this is the pz where the orbital lie directly on the z-axis. The orbital is lying on the z-axis. The x and y-axis are completely free. So that is your pz orbital. So these are the diagrams that I will draw later in the note. Px, py, and pz. Px orbital lie on the x-axis. This is the shape of the orbital. I had written it also. P subshell look dumbbell shape. So by dumbbell shape, this is what I had made. This is known as a dumbbell shape. Okay, so this is px lying on the x-axis. This is your py entirely lying on the y-axis, and this is the pz where the orbital is situated on the z-axis. So these are the three possible orientations. Other than these three, you cannot draw any other thing. So these are the three possible orientations of the p subshell. And these are the probability distribution. If you see the probability distribution, you see that the red and blue dots are just present directly on the x-axis. It is present on the x-axis. Y and z is completely free. Nothing is touching. So that is why this is px. For py, it is entirely present on the y-axis. X and z is completely free. And this is your pz. This is the pz. This is your pz. Where it is present entirely on the z-axis. It is looking like a dumbbell shape now from here. If you see, if you just draw all the points, if you join the point, then only you will get to this structure, to this type of structure. If you see it from this in a slightly aligned way, then you can get an idea of the dumbbell shape. You can almost get a dumbbell shape structure like this kind of dumbbell you are getting. Okay, so just join the dots and you will get to this structure. Obviously, you do not need to know the dotted structure. These are just for the sake of understanding. You need to draw this structure: px, py, and pz. So is px, py, and pz clear to everyone?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So px, py, pz. That means here the lobe lie on the x-axis or the y-axis or on the z-axis. That's it. Now what about the d orbital? Now in the d subshell I had told you, see in the note, that there are 5 possible orbitals. So the D subshell can have 5 possible orbitals, and the shape is double dumbbell shape. So double dumbbell shape. So let's open the D subshell. There can be 5 different structures possible for D. So the first structures that we are going to see is DXY. So let's first see DXY. So over here you can see in this DXY that you see that neither the lobes, and this shape is called a double dumbbell shape. This is a double dumbbell shape. You see none of the lobe touch the axis. Nothing is present on the Z axis. Z axis is totally free. See, nothing is present on the Y axis also. Y axis also completely free. X axis is also completely free. So nothing is present on the axis. Rather, it is present in between the two axes. It is present on the plane between two axes. See, you can see now in the position that I have taken the diagram, you can see the X and Y axis. And you can see all the 4 lobes of the d orbitals are present in the XY plane. That is in between the plane of the X and the Y axis. Right? It is present in the spaces between the X axis and the Y axis. So that is why this orbital is called DX1. That is why this is called DXY orbital. Okay. Then let's see the DYZ orbital. So similarly, over here also DYZ. In DYZ again, all the X, Y and the Z axis is free. Now see, let me take the Z and Y axis. See, you can see the Z and Y axis now clearly. And now you see the lobes of the orbital are present on the Z axis and the Y axis in the spaces between the Z axis and the Y axis. So it is present on the axial plane and not on the axis. It is present in the plane, in the space between the Z axis and the X axis. So that is why it is called DYZ. Then similarly, another possibility can be DXZ. So again, nothing is present on the axis. Rather, the DXZ is present in between the plane of the x-axis and the z-axis. So it is present in the axial plane between x-axis and z-axis. Okay, so that is the dxy, dxz, and dyz. So these 3 are of a similar type, while the lobes are not present on the axis. For the p orbital, we had seen that the lobes are directly present on the axis. But over here, in this 3, we are seeing that they do not touch the axis. Rather, they are present in the axial plane. Now let us see this one, dx square y square. So here you can see only the z axis is free. You can see the z axis. The other ones cannot be seen because over here the lobes lie directly on the z, x and the y axis. So the lobes are lying directly on the x and the y axis. So that is why you cannot see the x and y axis over here. What about the dz square? This is the shape of dz square. You see, you cannot see any of the orbitals. This is because the blue lobe is our z-axis. So the blue thing is the z-axis, and this red is called a ring of charge. This is the ring of negative charge around the axis. Okay, so that's now. What about, so is the shape of d orbitals clear to you? And these are the shapes that we are going to draw. X, Y, X, Z. This thing will be drawn. So is the shape of d orbitals clear to everyone?
Yes, sir.
Yes, sir. Then what about the F orbitals? F orbital, I told you that F orbitals are quite complicated. And for F, you have seen that there can be 7 possible structures for F orbital. And in the diagram only you can see it's very, very complicated diagram. Okay, because there are so many lobes to it. And it is not possible actually to draw in paper. You cannot draw an F orbital on paper. It's very complicated to draw. So that is why these are computer generated images. So these are just for the sake of seeing how the orbitals look. These things cannot be drawn on paper. So I will draw the S and the d orbitals, but not this, because these are very complicated. These are the shape of the F orbitals. Okay, so these are the 7 shape of F orbitals. and this is the last one, 2 lobes. So now let's draw the shape of the orbitals. So have you understood the 3D form of all these S, P and the D? Not the F. F you do not need to understand because it's complicated. Have you understood S, P and the D orbital, everyone? Has everyone understood the shape of the orbitals?
Yes,
Yes,
sir.
sir.
So then now let's draw it. Let's draw them. So now we will draw the shape of S orbit. S orbit. We have seen that S orbit is spherical, but obviously we cannot draw a sphere. We cannot draw a 3-dimensional sphere over here. So we'll just make it look like just a circle, although it's looking at it. So this is the shape of S orbit. As you can see from the shape that it's spherical. That for S only one type of S is only possible. You cannot have any other possible combination of S. Why is it so? Because it is a spherical though. So from whichever side you look, it is going to appear the same only. So that is why for S only one orbital is possible. That means only one orientation is possible. That is what only has seen for L is equal to 0, only one orbital. Now let us see when the shape of p orbital. So let's draw the shape of the p orbitals. Orbital. Let's first draw the axis. Obviously, these diagrams require practice, otherwise you cannot draw. Now, please draw in practice. This is the x-axis, y-axis, z-axis. You can select the axis at your own will. You can change the axis, whatever you like. Now, what is this px? So we will draw px. So the px orbital will lie on the x-axis. That is why it will look like this. We had seen the 3D dimensional shape already in that website. Here we just draw the diagram. Now, obviously, I cannot draw a 3-dimensional object on a paper. That is why it will look like this. For the py orbital, it will lie on the y-axis. Like this. And pz orbital is going to lie on the z-axis. This is your px, py, and pz. And this is the dumbbell shaped orbitals. So when we did yesterday azimuthal, I told you that I will explain the dumbbell shape later. Now you get to know about the dumbbell shaped orbitals. So this lies along x-axis. Lies along x-axis. Lies along y-axis. lying along the z-axis. So I hope p orbitals diagram are clear to everyone. Yes or no? The diagram of p orbitals clear to everyone.
Yes, sir.
So this is the px, py, and pz lying on the three different axes. Now let us draw drawing p orbitals are not that tough also. This requires basically practice. That is d orbital. First we draw two types of orbitals. That is, let's name them x, y, z. X, y, z has been nicknamed x, y, y. So let's first draw x, y. That means it will lie on the plane between the x-axis and the y-axis. Thus it will look like this. Shape of this xy. This is the dxy orbital. Square box so as to indicate that it is lying on the plane of x and y axis. It is lying on the plane of x and y. This is your dxy. Okay, we'll write the names later. Then let's draw the structure of dxz or yz. Let us draw dyz. For yz, first make the box, then it will become easier to draw. This represents the yz plane. This is the yz plane. Now draw the lobe over here in between. Although it shouldn't touch the axis. Make it touch the axis. So this is the double dumbbell shape of the dyz axis. Then what about the dxz? How to draw the dxz? This one looks very. So then about the xz will lie on the plane of x-axis and z-axis. Lie on this plane. Demarcating the plane in this way will make it easier to draw. one no. One no. So this is your dy. Yz and tx. Now let's draw the other two slopes. Other two, that is your dx square y square and dx. These are quite easy to draw. You see dxy, yz and xz are of one type and these two are of another. So dx square y square, that means it will lie on the axis only. Lie on the axis. X axis, y axis, z axis. Called the dx square y square. What about this? And we make that ring form. Rub it. This is the dz square. So over here I've changed the axis a bit. This is the z axis. This is the x. But you can do, I told you. So this ring is called a torus of negative charge. This ring is called a torus of negative charge. Ring is called torus of negative charge. Torus of negative charge. Okay, so a torus of negative charge. So from the d orbital diagram you can see that we have basically two types mainly. There are two types. That is the dxy, xz and the yz. These three types actually lie on the axial plane. They lie on axial plane. They do not touch the axis. Rather, they are present in the planes of the axis. Lie on the axial planes. Whereas x square, y square, and z square, these two orbitals, they lie along the axis. Lie along the axis. So is the shape of d orbital clear to everyone? Yes or no?
Yes,
Yes,
sir.
sir.
So the thing is, as you can see also, you need to practice this shape of orbitals. Okay. And can you visualize? I hope you can visualize them since you have seen the diagrams. You should be able to visualize the 3D form of the orbitals. Okay. So that is about the d orbitals. So and that's about our magnetic quantum numbers. So I think it's better to stop here today. And in tomorrow's class, we will try to write down the rules of writing electronic configuration. After tomorrow's class, then in the next class we will be able to write the electronic configuration of different elements. We are coming on to almost the end of the chapter. Today is Monday. So maybe either by this week or by the next Monday, we might even finish this chapter. We have almost come to the end. So is whatever that is taught today clear to everyone? Yes or no? Any doubts anywhere in this much? Any doubts anywhere?
No, sir.
No, sir.
Kindly read this thing in your home. You have the recordings also. So please read it and please be up to date. Okay? Because as you have seen that it's a very big chapter and you are reading it for many days. And there are many small topics inside the chapter. And you have to be aware of all the topics. You will be applying when you will be writing the electronic configuration. We'll be applying all these things. Principal quantum number, magnetic quantum number, all these concepts will be applied while writing the electronic configuration. So if your concepts about this thing should be very clear. That what is a subshell, what is an orbital, how many electrons can be present in an orbital, so how to find out the maximum number of electrons. Everything has to be applied while writing the configuration. Please be very careful while reading this chapter. Please be up to date with the class. Okay. That's all for today. We'll meet again tomorrow. So I'm disconnecting the call.